Luigi Martinelli is an associate professor in the Department of Mechanical and Aerospace Engineering at Princeton University. He studied aeronautical engineering at the Politecnico di Milano and obtained a PhD in computational fluid dynamics in 1987 from Princeton University. He currently teaches courses in fluid dynamics, aircraft design, and applied mathematics. Dr. Martinelli's research interests are in computational fluid dynamics and encompass the development of mathematical models, algorithms, and computer codes for the simulation of complex fluid flows on complex geometries, the design of efficient numerical algorithms for both steady and time-dependent flow and their effective or efficient implementation on massively parallel computers, and the efficient simulation of three-dimensional turbulent flows on aircraft components in subsonic, transonic, supersonic, and hypersonic regimes, as well as incompressible flow about ship hulls, which would have been of interest to Benjamin Franklin. In collaboration with Dr. Anthony Jameson, Dr. Martinelli has devised and implemented novel methods for automatic shape design optimization based on Reynolds averaged Navier-Stokes equations. Dr. Martinelli has co-authored 80 technical papers and presented regularly at the AIAA Aerospace Science meetings and at the AIAA summer conferences. And as you see up here, the title of Dr. Martinelli's talk is CFD in Aeronautics, a historical perspective. Gigi Martinelli.
Thank you. So preparing this talk has really been a humbling and very difficult task. Not only because, by revisiting the development of a field like computational fluid dynamics, I came to realize how fortunate really I was and have been in crossing the path with so many brilliant minds that really contribute to my development as a researcher and as a human being. But it's also the occasion of this talk is particularly humbling because I think that is honoring one of the true pioneers in CFD field, Professor Spalding, and really one of the most influential applied scientists of our time. So having said that, and the title is actually quite dangerous as well. So because if you look at it will take much more than 35 minutes allotted by this talk to actually do justice to the development of computational method within the framework of aeronautics. Here is only a list up to roughly 2,000 of the CFD review articles that have been that have been appearing on the annual review of fluid mechanics, and with very familiar names as author, and some of them will become even more familiar in this talk. So what I can do today, the only thing I can do is actually present a personal and necessarily incomplete view of the field from my viewpoint, which has always been for the past 20 years really more comfortable from the trenches of development than from the top. And of course, I'm indebted to many mentors and colleagues that have contributed to my development and provided some of the materials in this talk, in particular to Anthony Jameson and John Vasberg, with whom I collaborated regularly in the past years. So let me just finish my introductory remarks with this quote from Geer's book, which is one of the classical texts in numerical analysis, because there is really nothing more true than this statement that explains the development of numerical methods in aeronautics. So it basically means that the progression of numerical methods has been that originates with the engineer, could be a scientist or an astronomer, who solves this problem that was previously unmanageable. And then progress is made through mathematical analysis that proves that they do indeed solve the problem under some condition, and finish with the numerical analyst and computer scientist that concern himself with effective implementation and utilization of the computer. This one, in a sentence, in my point of view, is actually capture the essence of what happened in the field. So why we talk about aerodynamics as a special field? Well, because the development in aerodynamics and the problem of aerodynamics is a little bit particular. The needs are, like in other discipline, it depends on what you're looking for in your simulation, in your calculation. But as you well know, we can use in aeronautics a hierarchy of flow models and actually get some very useful information from simple scalar models such as potential equation. The other thing that is actually typical of aerodynamics is that we need to implement this method on arbitrary topology. Even a simple two-dimensional airfoil like that is presented the complication of a multiply connected domain, and therefore there are different strategies that you need to you could use and have been developed to deal with this particular problem. The third one is the fact that the drag, which is the measure that you are interested in if you're an airplane designer, require a high level of accuracy in your calculation. So we are not really looking at solving the flow field to extract the feature necessarily of the flow field or understanding the flow physics, but we really want hard fact, hard number. Is this design better than the other, and by how much, and what's the level of confidence in the drag prediction? And if it has to be used useful in a design environment, you pay a lot of attention on speed of execution and setup times, which basically means that how you set up this, the geometry meshing over this complex configuration. And you want to make sure that your implementation in software is robust in such a way that when you change parameters, you can anticipate in many respects what's going to happen. You don't want to have surprises. So as I mentioned before, one of the things that distinguish aerodynamics from other fields in CFD is the fact that we could actually get a lot of useful information from simplified linear or nonlinear model using the potential equation. And I put here on the left side of this pyramid roughly the times, the decades that have been dealing with this particular mathematical model. The beginning in the 50s and the 70s was all dictated on trying to solve the potential equation, which by this morning definition is not really CFD, but it was kind of very useful on actually designing better airplane. I personally would make the suggestion that we really, in this field, we start this traditional CFD when we deal with nonlinear problems. So the nonlinear potential equation, although it's a scalar equation, is a problem that cannot be solved by other means but numerical calculation. So if you want to draw some initial points for truly CFD in this area, most probably the nonlinear potential equation, full potential equation, is the place to put. And in the 90s, and more recently with the advanced or computational methods, we are routinely now solving Reynolds-Average-Navier-Stokes equation over complete configuration. And again, we are mostly concerned, as this is well known, by three-flow regime, in which, if you look at simply from the flow phenomenology and the characteristic of the potential equation, is the potential is either elliptic or mixed type in the transonic regime or hyperbolic in compressible regime. So we are really interested potentially in developing numerical algorithms for all the three possible kind of PDEs. So the first one was mentioned earlier this morning is panel methods, which is a boundary solution, a boundary method to solve basically the Laplace equation over complete configuration. Is the first. Is interesting because it actually developed and mainly from industry, within industry. The first report by Hess and Smith that there were Douglas aircraft is actually in 1962, and the effort by Paul Rupert and at Boeing started in 1964. And this one actually internal report that described the first attempt and the first successful methods, at least in the United States, of actually solving the potential equation by using boundary methods. And there is an excellent, I'm not going to talk about panel method, but I just want to point it out that there is a very well comprehensive and very well written review in Annual Review of Fluid Mechanics by Hess in about 1990. So, sorry. Really, when I would say that for us, the hardcore CFD was actually born with trying to solve what the solution of the potential equation in the flow in the transonic regime. That's what I call a transonic regime challenge, because is starting from 1956. It is well known that transonic flows that are of interest, because that's where you want to cruise more efficiently, and also that's where even a supersonic jet will maneuver. You know that from a mathematical point of view, they're very, very tough indeed, and if there are shock-free solutions, they're actually isolated point. What does it mean? It means that even if you can find a solution that has no shocks, and in the transonic regime, or a supercritical airfoil, if you like, then every single perturbation, either in the geometry or in the flow field characteristics, will move you away from that shock-free solution. That's a theorem that Kathleen Morawitz proved in '56, and actually highlights what are the challenges and difficulties of this particular regime. What they have here, the depiction that they have here, is actually a much later demonstration of the fact that in this highly nonlinear regime, there are non-unique solutions that can be found, both with the Euler equation, and this particular case of one airfoil that exhibit non-unique solutions, which basically means two different lift for the same angle of attack. But similar results were obtained before and shown before from the potential equation point of view. So it's important technically, and it's difficult computationally. The first attempt were actually in the early 70s, and the main actors were actually Earl Merman and Julian Cole, that in 1970, actually in the AAA meeting in January 1970 in New York City, presented the first really viable solution of the small disturbance equation in transonic flows with the associated linearized boundary condition. And there was also a paper by Yashihara at the same meeting, and that's where basically caught the interest on the industry and the interest in CFD at that level. And at the same time, Tony was back then in Grumman, and it was actually after being excited about what he has seen in the meeting in New York, he started coding his own methods, most probably on his own time, and really the first results that solved one of the major problems of the mixed type, so basically having the right region of influence for your numerical schemes, it actually was published in 1973 at the first CFD conference in Palm Springs, and is a paper by Jerry South and Tony that is actually the first publication of the rotated difference schemes. So the difference schemes actually allows you to upwind automatically in supersonic region and maintain the proper region of influence in the subsonic part. Fine, so at the beginning of the 70s, then that problem was solved, but really people were convinced that, rightfully so, that at least they needed to move to solve the full potential equation. And full potential equation, which is the full nonlinear isentropic picture of the flow, in that particular flow regime, the solution is complicated by the fact that the boundary condition cannot be linearized anymore, and therefore there needs to be enforced on curved boundary. And remember what I said before: if the boundary has to be represented fairly accurately, because the flow solution is going to be extremely sensitive to the accuracy of the boundary itself, for example. And so that basically force, or encouraged the use of body-fitted grid for the first time. And the other alternative would have been using interpolation formulas, but the field went on using body-fitted grid, which is great, eliminate the needs for destabilizing interpolation formula. The cons actually require a domain mesh. And so the entire field of gridding, of developing body-fitted coordinate in 3D opened up at the results of that. But for simple geometry, such as a three-dimensional wing, you can actually use conformal mapping at this level and generate a very good quasi-orthogonal grid that will do the job without being too involved with the mesh generation. And for what concerns the full potential equation is the two publications that really stands out are in the second Transonic symposium is actually, I think this one is not in Berlin. What the symposium was in Göttingen is Tony's paper on basically his approach to full potential. And for implicit algorithms, Terry Holst has a very good and influential paper a little bit later in 1979. So let me talk a little bit more about what has been a game changer in the field, and that's the computer code that implements the 1975 algorithms. And it was really a game changer in the field because it demonstrated, as we will see in a second, that computational fluid dynamics was a useful tool in airplane design. So I'm not going to go through these tidbits on how Flow22 came to be, but the important point is that it started coding almost like in 1974, and I sat on the boxes of Tony's office for a few months, and back then there were boxes of cards. For those of you that are young, most probably you've never seen that. They were actually physical ASCII cards, painfully typed on one of these puncher, and whenever you will give the box of cards to the operator, you almost had a heart attack because sometimes they would be jammed in the machine and then you had to start all over again. So, right? So that was basically the computing back then. But then these two boxes of cards sat in Tony's office for a while until David Coe of Cornell actually came into the picture. Back then Coe was actually a Douglas aircraft. And that when, after he moved to Cornell, he has actually got a copy from Flow22 and had it run it on the Cornell machine in a couple of weeks. David is a very good programmer. And that's changed the games because is actually the program was actually published and went around the world in this 1976 NASA report. And will produce, basically, this one is a typical on a wing, pressure distribution, including shock, weak shock. This is the lambda shock on the top surface. This is the bottom surface, over a three-dimensional wing. And as you can see that there were a few bugs at the beginning in the 76 paper, but this one, when all these little bugs were worked out, the pressure distribution was actually not that different, and the CL prediction and the CD prediction were actually agreeing within about 1% of each other. But there are a lot of people that contribute to in the industry to the development of Flow22. And 75 to 90, the enhancement on Douglas aircraft by Pressini, Pradeep, Raj, Lockheed added the multigrade acceleration. Lexia at Cornell, it did improve some transformation at the trailing edge, and that's basically is a reflection of this better pressure distribution right there. And John actually, Douglas aircraft implemented the flow in core. So it had a real industrial impact. In April '76, they were the first flow solution Douglas aircraft on DC-10 wing. This is the amount of plotting, automatic plotting that was available right now. And this one was the pressure distribution, the continuous line from experimental data, and this one were actually the prediction of flow 22. And the results was clearly Implicit potential obtained on a fairly fine mesh, about 150,000 nodes. And the computational cost for one calculation of this time on the IBM mainframe was about $8,000, and soon after was $3,000, which was peanuts with respect to what the impact was on the Douglas development back then. And it's still used. This one is a calculation that I obtained from John Vasberg in 2009. When you add a boundary layer correction to flow 22, then you basically look at the pressure distribution over a three-dimensional wing body configuration in the transonic regime as such, you can say that the pressure distribution, the drag and the lift, they're pretty much in agreement, except maybe the confluence of the shock with actually one of the most accepted tools, more modern tools, which is overflow, that solved the Reynolds average thin layer Navier-Stokes equation that has with an overset grid methods and require about 12 million points, and it takes about 300,000 CPU per second on a Linux cluster these days, and still flow 22 with a boundary layer correction gives a similar prediction in about 10 seconds on a desktop or desktop computer. So it's still a useful tool. I mean, we in industry right now, codes of this sort have taken their own right place, but still this very old code is very useful to the engineering, to the aerodynamic designer to actually do a quick study. So why do I spend so much time on this? It's because it basically was really a game changer, and I want to depict in this what actually took to actually change the field in aeronautics. It takes some visionary and people in many respects. The pioneering work of Norman Cole, the influence of Paul Garabedian and his group at NYU that were heavily involved in the development of the supercritical airfoil. You needed new computer hardware. You needed algorithms and computer, and you needed a developer. If you think back on the Gears book preface, that's exactly what it takes. There was a need, you needed to compute that, and a lot of things have to line up. And that's what happens. The net result for flow 22, and it was really a game changer and a paradigm shift in transonic aerodynamics in industry. It opens up future development on application of finite volume, both from the potential equation and later on to the Euler equation, and really enable transonic aero design to be carried out pretty routinely in the industry. So, what are the ingredients that goes into a numerical algorithms? Well, first of all, is you actually have any flow model needs to be discretized in time. And we actually have two classical techniques, finite difference, which I haven't put anything here because the list of reference on finite difference most probably needed to go back about 200 years. And in our community, the finite volume approach was actually popularized by Bob McCormack, and the paper by McCormack and Paul in '74 most probably is the one that is more cited in our community for what concerns the finite volume. And these two yellow ones are basically the two key references that they put finite element methods on the map in our field. And this one is Glowinski, Perrier, and Pironneau with collaborators in France. They were very active on using finite element for the potential equation, and 85. And this one is Reinhold Luhner, Morgan Pereira, and Sienkiewicz on 1985 that really put the finite element approximation on the map in our community. The spatial discretization, though, could not be successful unless you take care of a little, let's call it little detail, which is actually the necessity of actually truncating the computational domain in a computer code. And therefore, you need to make sure that you implement the boundary condition in the far field in a consistent and non-reflective way. And the problem is, it's fair to say, that was actually solved in '77, and everybody really refers to Enquist and Maida approach on actually developing a reflecting boundary condition in the far field. And that's the other key ingredient that allows us to actually complete the space discretization. The interesting things about the transonic or supersonic regime is that you have to deal with shock waves. And shock wave, from a physical point of view, you can think about it as a multi-scale flow feature, right? Because shock waves, the non-equilibrium readjustment of the flow takes place over a few mean-free paths, and you're interested in meters or tens of meters length scale of your aircraft. And so if you're trying to solve the problem on a large scale, you need somehow a way of representing the correct jump condition across a shock wave, and that's required basically that you do one of these two things. Either you're trying to capture the shock. Capturing the shock meaning require dissipation, because if you think about it, if you start from the Euler equation or even from an under-resolved Navier-Stokes equation, you need a length scale. And the length scale is going to be put somehow by some sort of dissipation in your scheme. Or else you can actually try to track down the shock and using shock fitting technique, which basically means enforce the correct Rankine-Hugoniot condition across the shock, but requires that you track the shock location. I'm not going to go into the detail of shock fitting. There is, I just want to point it out that there's a very new book that also has a very historical account of shock fitting technique by Manny Salas, and all this school that originated from Moretti and his co-worker. I'm going to spend a little bit more time on shock capturing, which is one of the techniques that is prevailing in the field, and really follow from the pioneering work of Goodenough. This is the first paper, 1959, that is referred to and is translated also in English. A Russian friend told me that some of this previous work was actually published in this thesis, PhD thesis in '56, but is only available in Russian. And required dissipation for shock capturing, and the dissipation must and can be controlled for accuracy in smooth motion on the flow. And that's where basically the idea of flux correct transport, which was pioneered by Boris and Book in 1973, comes into play. So throughout the years, there are a lot of techniques that have been developed and approaches. The most popular one are the muscle approach, Van Leer in 1979, TVD approach by Amy Arthur in '83, has been, in many respects, reworked out and extended and reformulated as a local extreme on diminishing schemes by Jameson. And the only difference between these two approaches is that they behave quite a little bit differently on unstructured meshes and in picking up ridges on a purely unstructured mesh. And then, of course, the essentially non-oscillatory scheme by Stanley Osher and his students and co-worker. So these are the key reference, I think, that corresponds to the construction of numerical algorithms for scalar conservation laws. And then there is also the other problems that once you know that your numerical schemes is actually non-oscillatory, capture shock, and your scalar conservation laws, you want to apply that to the flow equation, which is a system. And that's actually opens up the choices on flux splitting. And the flux splitting that have been successfully developed and used in the field are due to Steger and Worming. There is, of course, the characteristic variable work, which is most probably the most used at this point by Fierro. And there are two approaches that actually OSP and CUSP, which are very robust in practical application. Leo was at NASA Glenn, and Tony was at Princeton when we developed CASP. And CASP really is a reworking of something that was proposed and used by Denton in England for a long time, actually. The paper by Denton is 83. And so we have this discretization, and the next thing that you have to do is actually figuring out how to integrate, if you're interested in steady state, this flow solver. And most of the flow solver are going to be based on a time evolution. So you're going to write down your system of conservation laws in a semi-discrete form, in which you lump together all the flux balances, both from a convective and eventually from a diffusive point of view in this term R. And then you're trying to march these semi-discrete schemes to a steady state. All right? And here, again, you have certain choices that people have made and investigated. Clearly, if you think about it, if you don't want to destroy, the parallelism and that is there, inherent in any fluid flow, well, the simplest thing to do is actually having, an explicit scheme. And you have all the family of Lax-Wendorf, which are, very efficient methods for actually solving and advancing in time. But if you use them for solving to a steady state, then you know that there is a terms in the Lax-Wendorf scheme that depends on the delta t, and so your dissipative terms, and so basically your steady state will depend on the choice of the time step that you are doing, and this leads to the development of multi-stage time stepping schemes, which is one of the accepted way of advancing in time. The problem with explicit schemes is the fact that they're fairly slow. They require, all of them, a lot of time steps to reach a steady state. And so one thinks about, what about an implicit schemes? Well, if you think about it, an implicit schemes has its own problem. Because even if you discretize this equation by an implicit schemes, you should, and by backward Euler, for example, in time, you should compute your residual, or basically your fluxes, at times level n+1. Well, these fluxes are actually nonlinear. So solving this particular equation requires some sort of iteration, right? Because it's a nonlinear set of algebraic equation. And so you come back to this paradox, right? That the time evolution methods to find a steady state is an implicit method. Suppose that you want to do that, which allows larger time step, would be preferable. But the implementation of an effective implicit method requires a fast steady-state solver. So accordingly, a fast steady-state solver is an essential building block for an implicit scheme. And that's basically is the paradox that is there in every single implicit schemes for nonlinear equation. And that's basically what forced, particularly our groups and many others, to look at the way of developing numerical methods that actually accelerate to the steady state. And this brings up to the development and use of multigrade technique in our field. Fedorenko was the first one to actually propose multigrade in '64, Archie Brand in '77. Ronnie in our field, United Technology, brought in multigrade to the other equation, and it became part of our family of schemes. So I'm running out of time, but I just wanted to have you a very quick view on how the field developed, and why, in many respects, developed this way. So let me jump to, if I find it, to forward in time, and basically tell you a little bit on where the field is right now. So right now, I think that it's fairly reasonable to say that CFD is a mature and accepted technology. We have developed numerical methods that allows you to solve really complex flow, at least from the Reynolds average point of view, on very quickly. And that has brought really the appetite for even more complex configuration. So you really want to do full configuration of aircraft, rotating blades, and so on and so forth, which basically force you on actually implementing complex code which requires large teams. So we are almost in a situation in which designing a better wing, it takes less people than actually maintaining one of these codes. So basically, along this line of development, CFD has become mostly a software engineering problem. And the codes that actually are in use and developed are necessarily by bigger organizations. There is CFL3D from NASA Ames. There is Overflow from Langley. One is Thomas and Ramsey. Overflow is Peter Buning and Jesperson, and reincarnation, and embedded, Arc2D and Arc3D of Steger and Pulliams, and all the experience in NASA Ames. And in Europe, you have things like, the Tau code that is at DLR. And so basically, the research in of new direction that has been followed in the late 90s and today is actually toward trying to use, and we are successful in using CFD as an inner loop for optimizing shape of an entire wing body configuration, and we are able to get more efficient aircraft in cruise condition pretty automatically. Multidisciplinary optimization is the area in which you're trying to link basically the fluid mechanics to structural constraint and other mission constraint. And on the CFD research, really the field has moved toward time-dependent, research on time-dependent algorithms and pushing, more high-fidelity fluid structure interaction problem. And there has been a little renaissance in the past 10 years on actually looking again to higher order methods, discontinued Galerkin for one, or spectral differences. And that's basically where the field is right now. I have one more slide, and I'll. So the kind of things that you can do is actually improve aircraft design, and that has been done. And by concluding, I can say that in our field has been driven 40 years of relentless progress in CFD, really, for compressible Reynolds average Navier-Stokes equation. And the question is, therefore, are we completely done in this field? It's a mature field. If you look at it from an industrial point of view and in a cartoon manner, and if you map on the vertical axis, wind tunnel hour that are spent in some part of the design, you're going to find out that the high-speed lines, which is basically the cruise condition, which is the problem that we are able to tackle and solve routinely right now at a very high level of fidelity, is only a small portion of the problem. And CFD has had little or no penetration in high lift design, in basically certification for the aerodynamics load. This is done still by wind tunnel and flight test, flight simulator, and especially for the design of the control system. So this one, if you think about it, is an area in which you need high accuracy, you need high turnaround time, and you need unsteady and possibly aeroelastic coupling. And that's where basically the field is and the leading edge research. I'm sorry that I took five minutes more, but I conclude here. Thank you.